Okay, hi everyone. Welcome back to lecture 22. Sorry the live lecture got cut off today because the annotator wouldn't work, but I'm going to record this and just upload it for you. And it should be a little shorter than the regular 50 minutes. So let's begin. Today we're talking about viscous flow in pipes, and we're talking about the difference between laminar and turbulent flow, and a couple of other items. So I'm going to switch over to the annotator now. Which is now miraculously working. Right. Okay. All right, so here we go. So here's a typical engineering system of pipes, right? We've got a pipe system that's pumping water from some lower reservoir to some upper reservoir here. It goes through a series of turns. It goes through a pump, goes through a T-junction. There's a valve here, lots of different pipe components. And what we're going to find is that there are two types of losses associated with pipe systems: major losses and minor losses. And the major losses are just due to actually friction against the walls from the fluid traveling through the pipe system. That's the majority of the losses usually. And then the minor losses are due to things like the pipe taking a 90-degree turn or going through a valve or a fitting, something like that. And those usually have a loss coefficient associated with them. Those are called minor losses. One thing we're going to assume in all of this pipe flow is that we're dealing with a closed pipe, closed container, so that we can develop pressure differences between different sections, and also that the fluid completely fills the pipes. So we're not dealing with open channel flow, but the pipe is completely filled. So just now starting to look conceptually at the difference between laminar and turbulent flow in a pipe. If you imagine you've got a pipe here and you've got flow from left to right, and you stick a needle in and inject dye right at the center line. If you've got laminar flow, it's generally slower flow. And what happens to the dye is it just makes a nice, neat, tidy, straight line as it advects down the axis of the pipe. If you raise the velocity in the pipe a little bit, you'll have that nice, straight, smooth line, but then every once in a while, you'll have a little hiccup, little sort of random behavior. If you raise the velocity even more, then you're in the turbulent flow regime. You inject dye, and you can see the streamlines, the streak lines of the dye are just chaotic, and they trace out three-dimensional paths, right? And that's really what characterizes turbulence, is that chaotic, random, small-scale motion. So coming over to the right side here, we get the same pipe with the same flow rate through the pipe Q. If we take data at one point A, if we record the axial velocity versus time, like we've got over here on these axes, for laminar flow, you're going to see just a nice constant value for the axial velocity at point A. If you increase the flow rate, and so we're in the transitional regime, you'll see mostly a constant value, but then some hiccups every once in a while. And if you can increase the flow rate more so that we're in the turbulent flow regime, you've got this chaotic motion. And that's what your velocity signal looks like. All right, another thing to think about, other than whether the flow is laminar or turbulent, is whether the flow is so-called fully developed, right? So if you look here at this pipe system, we've got fluid entering the pipe from this large reservoir. The fluid's shaded pink here. When it first enters, you've got this uniform velocity profile, but soon enough, viscosity from the wall starts to eat away at the edges of that profile, and because of the no slip condition that says that the velocity has to be 0 right at the wall, you end up with a velocity profile that looks like this. You've got a so-called boundary layer growing in from both the top and bottom walls. Of course, this isn't top and bottom. This is an axisymmetric system, and we're just looking at a slice. And that boundary layer is going to grow and grow from all sides until it meets in the middle. When it happens, the entire flow field is completely viscous, and the flow is what's called fully developed. And you've got this nice characteristic parabolic velocity profile that we expect for a laminar pipe flow in a straight section of pipe, for fully developed laminar pipe flow. So this is called the entrance region from sections 1 to 2. And then from sections 2 to 3, we've got this nice fully developed flow. We've just got this nice parabolic profile. It looks the same all the way in this region. Then at section 3, we kind of mess things up again by taking this 180-degree turn, and that applies an acceleration to the fluid, right? So then it takes some time to recover again from sections 4 to 5 and become fully developed again, right? It's fully developed, steady flow. From 5 to 6, it's fully developed, and then you can see at 6, it takes another turn, right? So how do we know when the flow is fully developed? Well, there we can calculate the so-called entrance length for the flow. So for a laminar pipe flow, the expression for the entrance length over the diameter of the pipe is just 0.06 times the Reynolds number, which we'll get to in a moment. For a turbulent pipe flow, the entrance length over the diameter is equal to 4.4 times the Reynolds number to the 1/6 power. Okay, and the Reynolds number is a really important quantity in fluid dynamics. It tells you whether a flow is laminar or turbulent. It's defined as the density rho times some characteristic velocity in the system times the characteristic length scale over the viscosity, or equivalently, that same characteristic velocity scale times the same characteristic length scale for pipe flow, that's the diameter, over the kinematic viscosity. And this is the Reynolds number. And it turns out for pipe flow, for a given Reynolds number, we can say whether the flow is laminar, transitional, or turbulent. And let me just write those down here. So for a smooth pipe, we have laminar flow for a Reynolds number less than about 2100. We have transitional flow for a Reynolds number between about 2100 and 4000, and turbulent flow for a Reynolds number greater than about 4000. This can vary if the pipe is very rough. That tends to drop the Reynolds number at which it transitions. But in general, if we can assume that the pipe is smooth, these are the numbers that we use. All right, so let's write down an expression. Let's develop an expression for the flow rate through a horizontal pipe. So to do that, let's look at this pipe section here. We've got this nice parabolic velocity profile, so that means we've got fully developed laminar flow in a pipe. And we've got a pipe with a diameter d, and we've got a cylindrical fluid element. It's shaded in pink at time t. At time delta t later, it probably looks a little bit like this dashed outline, right? But for now, let's imagine what the forces are acting on that fluid element. So we've got our viscous force that always acts opposite the direction of motion, and we've got our two pressure forces if we ignore gravitational effects for now. So here we've got tau, our shear stress, times 2 pi RL. That's that cylindrical area. And then we've got our pressure force, P1 minus delta P times pi r squared. And then the pressure force of the other one is P1 pi r squared. Right, so here are the forces. We're assuming that the flow is steady, fully developed. And we're neglecting gravity. All right, so now summing the forces along the axis of the pipe, we get P1 pi r squared minus P1 minus delta P pi r squared minus tau 2 pi r L equals 0, or delta P over L, the length of our cylindrical fluid element, is equal to 2 times the shear stress over the radius of our fluid element. And this is equation 8.3 from the textbook. Since delta P and L are not functions of R, the shear stress over R must also be independent of R. So 2 tau over R must also be independent. And that gives rise to the following expression, that tau is equal to 2 times the wall shear stress times R over D. This is equation 8.4. And just reminding us, tau wall is the wall shear stress. All right, so from here, combining equations 8.3 and 8.4, we can determine that delta P, the pressure drop along the cylindrical fluid element from one end to the other, is equal to 4 times the length of the fluid element times the wall shear stress over the diameter of the pipe. Okay, so what we can see here is that even a small wall shear stress can produce a really large pressure drop if the pipe is really long, right? So if L over D is 10 or 100, something like that. All right, so for laminar flow, we know that, and we'll just refer ourselves back to section 1.6, that tau is equal to mu, the viscosity, times du dy. If we now put this in terms of R and not Y, we get that tau is equal to minus the viscosity du dr. And this is equation 8.6. And you can do this just if you switch variables from y to r over here, but also it makes physical sense, right? Because we need a positive shear stress for du dr less than 0, right? So as you go from the center line of the pipe, as r increases, the velocity decreases, right? And so we get a negative sign there, but we need a positive shear stress at the wall. So everything checks out in terms of the physics. All right, now if we combine equations 8.3 and 8.6, we get du dr is equal to minus delta P, that pressure drop, over 2 mu L all times R. So we can integrate that in the following way. Du is equal to minus delta P over 2 mu L, the integral of R dr, or equivalently, U is equal to minus delta P over 4 mu L times R squared plus C, where C is a constant. Since the velocity is 0 at the wall, at R is equal to D over 2, by the no slip condition, we find that C, let's call it C1, is equal to the following expression. Delta P over 16 mu L D squared. Right. So then this gives us U as a function of R is equal to delta P D squared over 16 mu L times 1 minus 2R over D squared, or we can use this to define the centerline velocity. V centerline times 1 minus 2R over D squared. This is equation 8.7. And just a note about V centerline here. And V centerline is literally what it sounds like. If you go right to the middle of the pipe along the central axis of the pipe, that's the magnitude of velocity there, V sub C. Okay, we can also write this in terms of the shear stress. So U as a function of R is equal to tau W, the wall shear stress, times the diameter of the pipe over 4 times the viscosity, 1 minus R over big R squared, where of course big R is just the radius, half the diameter. All right, finally, we can integrate this velocity expression across the cross-section of the pipe to get our volumetric flow rate. And this is what we get when we integrate the velocity across the cross-section. We get this expression for Q, which is pi, the radius squared, the centerline velocity, over 2. Okay. Now, by definition, the average velocity is the volumetric flow rate divided by the cross-sectional area. So we have the average velocity V equal to pi radius squared centerline velocity over 2 pi radius squared, or it's equal to the centerline velocity over 2, right? So very important, the mean velocity, the average velocity in laminar pipe flow in this parabolic velocity profile is the centerline velocity divided by 2. This is equation 8.8. And we also have, for the volumetric flow rate, that Q is equal to pi d to the 4th power times the pressure drop delta P over 128 mu L, the viscosity, times the length of pipe. And this is equation 8.9. This is a really famous result. It's called Poiseuille's law, right? And it describes the flow, laminar flow of a fluid through a pipe. All right. Now, what if our pipe was not horizontal, but it was at some angle theta, like we see on the bottom right here? We can derive a similar expression in the same way. We'll go through all the details this time, but if we do a force balance, it's going to give us that delta P minus gamma times L sine theta over L is equal to 2 times tau over R. This is equation 8.10. And we can use that to derive expressions for the mean velocity and the volumetric flow rate Q. So the mean velocity is delta P minus gamma L sine theta times d squared over 32 mu L. Equation 8.11. I'll box that. That's pretty important too. Anytime you've got a pipe at some angle, you'll need this equation. And similarly, Q is equal to pi delta P minus gamma of the fluid times L times sine theta, all times d to the 4th power, all over 128 mu L. And that's equation 8.12. Okay, derived in the same way that we derived it for the horizontal pipe, except now, of course, you've got force components involving sine and cosine of theta. All right, one last thing to talk about. We've derived now for laminar flow through a pipe, we've derived an expression for the mean velocity. We've determined how the magnitude of the maximum velocity, that centerline velocity, relates to the mean velocity. It's actually twice the mean velocity. And we have an expression for the volumetric flow rate Q. We want to just talk about losses in laminar pipe flows. So writing down the energy equation between sections 1 and 2 in this figure here gives us the following. P1 over gamma plus alpha 1 V1 squared over 2G plus Z1 equals P2 over gamma plus alpha 2 V2 squared over 2G plus Z2 plus HL, the head loss. Okay. And just a reminder, alpha 1, alpha 2 are kinetic energy coefficients that compensate for the fact that the velocity profile is not uniform. So if you have a uniform velocity profile, alpha 1, alpha 2 are just 1. If you have a non-uniform velocity profile, for example, parabolic velocity profile, then they are greater than 1. And that's, you can look at the discussion around equation 589. All right, so the velocity profiles are not uniform, but they also don't change from section 1 to section 2. So that means that alpha 1 is equal to alpha 2. So this gives us the following expression: P1 over gamma plus Z1 minus P2 over gamma plus Z2 is equal to the head loss, right? So now combining, this is 822. Combining 810 from the previous slide and 822, we get the head loss is 2 times the shear stress tau times L over gamma of the fluid times R, which can be written in terms of the wall shear stress like this. 4 times L times the wall shear stress times gamma times D. And this is equation 823. So what we see here is that tau, the wall shear stress, right, which accounts for friction at the walls, is really what contributes to head loss in these pipe flow systems, the loss of energy. Moving on. All right, now let's talk about turbulent pipe flow, right? So first, let's just imagine that we have the flow through a pipe. Again, it's a horizontal pipe. The flow is left to right. We start with the fluid at rest at time 0, and then we start time running, as you see on the horizontal axis here, and we measure the velocity again at a point in the pipe, and what we see is this. As we increase the velocity, first we have a nice smooth velocity, and then the speed in the pipe gets so high that we start to get these bursts. We're in the transitional regime now. And then finally, we've increased the speed so much, we've got such a high flow rate through the pipe that we've got completely turbulent flow, completely randomized by these chaotic streamlines, right? We've got these random turbulent fluctuations. Notice the 3 regimes here, right? So on our right vertical axis, we've got the Reynolds number, and while the flow is completely smooth, we've got our nice laminar flow. In that regime from about 2000 to 4000, before we said 2100 to 4000, you know, this isn't very precise. These are just rules of thumb. We're in that transitional regime, so mostly smooth with a couple of hiccups. And then above 4000, we're completely chaotic streamlines. If we were to zoom in on the turbulent, if we were now to stop the speed, so we've got a very high flow rate through the pipe, and we're in the turbulent flow regime, and now we look at the velocity, u, the axial velocity at a point as a function of time, the signal looks like this, right? It's that chaotic signal that we saw from the previous page. Well, we can think about this in terms of a mean and a fluctuating component. So if we average over one time period, capital T, if we average this signal, then we get this mean value represented by this line, this bar, right? So we can actually write down our velocity in the following way. We can say our velocity is equal to a mean component plus a fluctuating component. And then we find the fluctuating component by simply subtracting the mean from the whole velocity signal. Right, and this kind of decomposition is really fundamental in turbulence. So when you start getting into computational fluid dynamics, if you're dealing with turbulent flow, one of the least computationally expensive ways to compute a turbulent flow is to just calculate the mean turbulent flow and ignore the fluctuating components. It's not as accurate as if you include them, but it's a very common thing to do, and it's called Reynolds average Navier-Stokes calculations. All right. Well, we had that nice parabolic velocity profile for laminar pipe flow, fully developed pipe flow. We have a counterpart that's often used for turbulent, fully developed pipe flow, right? So it's often written in terms of a power law velocity profile that governs the mean component, right? So the mean turbulent velocity divided by the centerline velocity is 1 minus r over the radius to the 1 over n power, where n is an exponent. And it's actually a function of the Reynolds number. And we often use n equals 7. And in your textbook, you've got figure 817 that gives you n as a function of Reynolds number. So if you've got a problem to solve and you know it's turbulent pipe flow and you're asked something that involves the velocity profile, if you can calculate the Reynolds number, you can find the appropriate n and you can plug into this velocity profile and find an expression for it. So just something to note, right? So this velocity profile looks a lot like the velocity profile for our parabolic flow, right? The difference was for the parabolic flow, we had 1 minus r over r squared, right? Which gives us a parabola like we see down here, right? This power law turbulent velocity profile looks more like this. It's got a higher centerline velocity, but it drops off more rapidly near the wall. So it's more of a flat plug-like shape. And that's because the turbulent motions are really energetic and chaotic, and they can actually overcome the viscosity a little bit better in the margins. All right, now if we just look at the upper half of this velocity profile, we get figure 818 from the textbook. So here on the horizontal axis, we've got the mean velocity divided by the centerline velocity. And on the vertical axis, we've got the normalized radius. So here we've got the pipe centerline. And if we go up here, we're at the wall of the pipe, the top wall of the pipe. Right, so again, here we've got our laminar velocity profile. It's that parabolic velocity profile. And just to compare on the same axes, we've got our turbulent velocity profile with 3 different values of n, right? N is equal to 6, 8, and 10 over here. So you can really see that that turbulent velocity profile sort of fills in the corners much more than the laminar one does. All right. Let's go through a couple of examples and we are done. So we have an oil with a viscosity of 0.4 Newton seconds per meter squared and a density of 900 kilograms per meter cubed. It flows in a pipe with this given diameter of 0.02 meters. What pressure drop is needed to produce this flow rate? 2 times 10 to the minus fifth. If the pipe is horizontal and x1 is equal to 0 and x2 is equal to 10, right? So we know the positions of our two sections, sections 1 and 2, and we want to find the pressures there. All right, well, if the Reynolds number is less than 2100, we can assume the flow is laminar, and we can use the equations we developed for laminar pipe flow. So the first order of business is to compute the Reynolds number. So the average velocity, of course, is equal to Q over A. And we have all of these quantities. So Q is 2.0 times 10 to the minus fifth meters cubed per second. And since it's a pipe, since we know the diameter, we know the cross-sectional area. So the mean velocity for this pipe flow is 0.0637 meters per second, right? So now the Reynolds number can be calculated. It's rho mean velocity pipe diameter over fluid viscosity. So we know that that's 900 kilograms per meters cubed. We just calculated the velocity. It's 0.0637 meters per second. And we were given the diameter. It's 0.020 meters. And our viscosity was also given. It's 0.4 Newton second per meter squared. So this gives us a Reynolds number of 2.87, right? A really small Reynolds number, definitely less than, a few orders of magnitude less than 2100. So the flow is definitely laminar. That's great. That means we can now use those expressions for laminar pipe flow, expressions for the mean velocity and for Q. All right. So doing that, taking equation 8.9 with L equal x2 minus x1 equals 10 meters, we get delta P, which is that P1 minus P2 we're looking for, is equal to 128 mu L Q over pi d to the fourth. We can plug in all those numbers that we have, and we get 20.4 kilopascals. All right. So there we go. Just to recap, first thing we did was check to make sure the flow was laminar. Since it was laminar, we could go ahead and use those expressions, Poiseuille's law, most importantly, that relate the pressure drop delta P with the flow rate Q and the diameter. All right, one more example. Now we've got a turbulent pipe flow. So we've got water at pretty much standard temperature with the following density and kinematic viscosity, flowing through a horizontal pipe, which has a diameter of 0.1 meters with a flow rate of 4 times 10 to the minus 2 cubic meters per second, and a pressure gradient of 2.59 kilopascals per meter. Determine the centerline velocity, the approximate centerline velocity. Now, in the case of turbulent flow, it's approximate because we're going to be working with that expression for the velocity, which is not exact, which only gives us the mean velocity component for the turbulence, not the whole velocity signal. So that's why the word approximate is used here. All right, so we can determine the centerline velocity from the average velocity. And we also have to assume a power law velocity profile. All right, so writing down just our very fundamental definition of the average velocity, Q over A. Here we have 0.04 meters cubed per second divided by pi times 0.1 meters squared over 4 gives us 5.09 meters per second. Call that equation 1. We've got to double check the Reynolds number, make sure we've got turbulent flow. So the Reynolds number, the simpler definition is average velocity times pipe diameter times over kinematic viscosity. So we've got 5.09 meters per second times 0.1 meters for the diameter over 1.004 times 10 to the minus 6 meters squared per second. That gives us 5.07 times 10 to the 5th. And this is definitely a turbulent flow because remember, for pipe flow, a Reynolds number above 4,000 is classified as turbulent. All right, call this equation 2. And we've got a second page for this problem here. Now we need to take that Reynolds number we've calculated and go to that figure 817 and figure out what the appropriate n value is, that exponent for the power law velocity profile. So we've got the velocity, the Reynolds number of about 5 times 10 to the 5th. So we go over here, here's 10 to the 5th, 2, 4, 6, 8, 10, right? So 5 is around here, or pardon me, around here. And we trace that back to the vertical axis and get an n of approximately 8.4. So plugging this into our power law velocity profile, doesn't like me writing close to the edge here. Let me go in a little bit. One minus r over r, 1 over 8.4. Call this equation 3. So now we can integrate 3 in the following way. And we get 2 pi r squared v centerline times n squared. Notice we went back to using the general form with n instead of using 8.4 in place of n, over n plus 1 times 2n. plus 1. Now, plugging in that value, it turns out that the centerline velocity is just about 18% larger than the mean velocity. If you contrast that with laminar pipe flow, if you remember, it was twice, right? Here we've got just about 18% larger instead of 100. So using our velocity value of 5.09 meters per second for the mean velocity, we get 6.04 meters per second for the centerline velocity. And that's our turbulent flow example. Okay, couple of reminders, video project proposals, just half a page due tonight at midnight. Go to the week 9 module to upload them. Only one person in your group needs to upload the proposal. And we are continuing to talk about viscous pipe flow this week. That's it. Thank you guys.